Okay, so we're going to look at sample problem 12.3. Now, over on the left-hand side here, you're going to notice that we have two blocks. We have block A, which is 100 kilograms, and it is on a horizontal surface. And then we've got block B, which is 300 kilograms, and it is hanging down from the pulley arrangement that we see here. Okay. The sample problem 12.3, the problem states that, and I'm going to go underneath here because they don't have the full problem statement on that slide. So we've got the two blocks and they're shown right now. They start from rest. The horizontal plane of the pulley is frictionless. So we aren't going to be worrying about friction between block A and that horizontal surface that it's riding on. So we're going to consider it negligible. Okay. The pulley is assumed to also have negligible mass. So the pulley here, which is a movable pulley, so this pulley would move up and down as this would, go back and forth. It is considered, negligible mass, so we don't have to worry about its weight or mass. It says they wanted us to determine the acceleration of each block, so the acceleration of A, acceleration of B, and the tension in the long cable and the cable, the little short one here that's connecting block B to the pulley above. Okay, so tensions in those two cables as well as the accelerations on each one of those blocks is what we want to find. Now, something I want to show you, and I'm going to go back to the illustration that they have here. Something that I'm not going to do that the book did, and it's going to change some of the signs of our values if you're comparing along the way. They have their convention where they have positive X to the right and positive Y down. We're going to keep positive Y going up. Okay, just to be consistent with like the rest of the world and all the other problems. Yes, you can do this, but it's just kind of one of those things that it's a negative direction on one or two variables. So I don't feel the need to confuse things by doing it. All right. So that's going to be the one thing that I do differently in this example than what the book does. So again, if you compare your values back and you're wondering why there's a change in some of the signs of some of the variables or the values, it's going to be because of that in the Y direction. Okay. So we're going to go with a traditional positive Y. So using this problem statement, what we are going to be doing is we're going to be approaching this by creating free body diagrams of block A by itself, block B by itself, and because we're interested in the tension on the cables, we're also going to be looking at that pulley, okay? So the first one we're going to start with is going to be block A. So let's kind of get our business going here. So I've got the start of my problem, sample problem 12.3 here. I do have my convention going up and to the right as positive. Okay. And I'm going to continue to be consistent with that. We need to find, I'm going to put that right up here at the top. We need to find the acceleration of block A and the acceleration of block B. And then we need to find the tension in cable 1. That is going to be the long cable. And then T2 is going to be the tension in that little short cable by block B. Okay. Okay. So we're going to be starting here with block A. All right. Now we're gonna draw it in that same form that we had on our last one. So this is going to be sum of the forces in the X equals the mass times acceleration. So we're going to have two blocks, if you would, on either side here. So for the first illustration with the forces, I'm going to start a little bit over to the left here. Here's kind of my center of gravity. My weight, oops, I didn't go in line here. My weight is going down. And that's going to be of A. That means the normal force is going up here. Hope you can see that. Look how that turned out. All right. This is 100 kilograms. That's its mass. And then it has the tension in that cable. So T1 is going to be the long cable coming off of A, which is going to go around the pulley. Okay. This is going to be equal to, we're going to redraw our block. Okay. And this is again 100 kilograms. And our motion is going to be mass A times acceleration A. So on the left-hand side, we have summation of the forces in the X equal to mass A times acceleration A. Now, as we look at the forces that are acting on the left-hand side, some of the forces in the X, there's only one in the X direction, and that is going to be T1. So we can say that T1 is equal to, we know that the mass of block A is 100 kilograms, so we can put 100 here, and the acceleration multiplied by the acceleration of A. I just remembered I forgot to do something, but it's going to be okay. I forgot to kind of look at our units of what we have here to make sure that they're all in the proper units before we go forward. So we do have everything in mass in kilograms for the metric. And then as we go forward, there really wasn't anything else given to us in the problem that would be anything but meters and seconds. So just so you know, we are good on our units. We didn't check them, but we don't have anything to convert. So now, as we look at this equation here, this is as far as we can go with this. There's two unknowns in this one equation, so we've got to kind of let this one sit. So then we're going to look at block B. And we're going to really do the very same thing with block B. So I'm going to draw block B on that left-hand side, same thing. Let's kind of bring block B back. Okay, block B is right here. So it is vertical. It's being held vertical. So there's going to be a tension. This is going to be tension 2 because it's the short little cable. Tension 2 going up. And then we have the weight going down. Okay. So at the center here, this is going to be T2 going up. And then the weight is going to go down. Now, the motion is in the Y direction, okay? And what we're given in this problem is that the mass of block B is 300 kilograms. So we need to calculate its, oops, I'm so sorry. We need to calculate its weight. We need to calculate its weight. So over on the left-hand side, I'm just going to do that over here. So the weight of block B is going to be equal to its mass times gravity. So we know its mass to be 300 kilograms times 9.81. Okay. So multiplying those two together, it's going to be 2940 newtons. Okay. So that's going to be 2940 newtons going down. Okay. Then we're going to set that equal to same block, okay? And here's its center of gravity, 300 kilograms. And we know that the mass of B times the acceleration of B is going to be going then down, sorry. Okay. All right. So now we're going to say sum of the forces in the Y equals mass B times acceleration B. So looking at our sum of our forces in the Y, we've got T2 minus 2940 is equal to 300 times the acceleration of B. And again, this is as far as we can go, okay? So we can put a little cloud around each one of these because we'll be coming back to these. Now, in the case of these two equations, you might be like, oh, we've got two equations. We've got four unknowns. So unfortunately, it's not a substitution that we can do yet. All right. If we have four unknowns, we need four equations, right? We only have two right now. But we've got a pulley. Let's see what we can come up with for the pulley. So we're going to do a free body diagram of our pulley. Okay. That is going to look like this. Okay. We've got going down. This is going to be the tension 2 going down to block 2. And then we've got a tension 1 and a tension 1. So if we look back at that pulley, the pulley that we're referencing is this one right here. Okay. So we've got a tension 2 going down and the 2 tensions going up on either side. Okay. Now they're telling us that the pulley's weight is negligible. So it's kind of like it's not moving. We're not worried about its mass or anything like that. So that means that we're not going to set it equal to anything. This is just going to be a sum of the forces in the Y equals 0 because it's considered not moving because it told us in the problem that its mass was negligible. So mass, if you would be 0. Okay. So multiplying by, even if it was moving an acceleration, it's 0. So when we look in this direction, we're going to have 2t1 minus t2 is equal to 0. So I like getting single variables on one side if we can. So I'm just going to push the negative 2t1. So I'm going to have negative t2 is equal to negative 2t1 because I'm moving this to the other side. And then they both become positive. Then I have t2 is equal to nicer format when we're trying to solve for multiple variables. So now if I look, the 3 equations that I have, because I got to stop there as well, I've got the 4 variables. Now, what we want to do is we want to try to have 2 of the equations to have 2 of the variables and the other 2 equations to have the 2 of the variables. So right now we can see that we have T1 up here and we have T2 down here, or I'm sorry, T1 down here. So it's in 2 equations. Perfect. If I look at acceleration of A, it's only in this one. I needed another equation. All right. T2 is in 2 equations, so that's in good shape, but the acceleration of B is also only in 1. So I need another equation with acceleration. All right. So turn this over. Another relationship we have with these pulleys, okay, based on the way that the pulley arrangement is. Now, chances are in your physics class, you probably had a pulley lab, right? You set up pulleys, put them in a couple different ways, probably block and tackle, movable, stationary, all that kind of stuff, okay? And you saw the mechanical advantages that arose. You not only saw mechanical advantages as far as the forces that were input that you could gain, but you also saw distances change, right? Your give up was usually distance. If I didn't have to pull very much and I could, pull on my pulley string and I was lifting a large load with a small amount of force, the difference was I had to pull a lot of string through my fingers for that only to go up a little bit. Do you guys remember that? Okay. And that all was dependent on how many wraps around my pulley there was. Okay. Now, if we look here, this pulley right here, if I cut this off, notice that there are 2 supports. Okay, so my mechanical advantage is a 2-to-1. So force-wise, my advantage would be I'd only have to have half the amount of force here to lift over here. Okay, but distance-wise, it means that when I'm pulling, if you would, along the tension of T1, I have to pull twice as far in order to get this to move up a little bit. So B is only going to move half the distance of what A is moving. Does that make sense to everybody? Okay. So do you remember first night of dynamics where we said, if we start with distance and we take 2 derivatives, we get to acceleration? That was the whole point of that conversation I just had with you, or that concept, okay? So we're going to start with the distance relationship here between block A and block B, okay? So I can say that the distance, we're going to call it X. I know B is in the Y direction, but we're just going to have a generic value of X for distance. The distance that B moves is going to be equal to 1/2 the distance of A. And again, it's because of the wrap around this pulley. When I pull A, if I pull 1 foot with, if I pull I'm going to say 1 meter of A, I'm only going to move a 1/2 meter up of B. Okay. So B's distance is 1/2 of whatever we move A. Does that make sense to everybody? That's the relationship here. So this is distance. Okay, that's distance. We need to take 2 derivatives to get down to acceleration. Okay, so the first derivative that we're going to take is going to be dxb over dt. And that's going to be equal to, I'm going to take 0.5 instead of 1/2. And that's going to be dxa over dt. This is your velocity of, the velocity of B is going to be equal to 1/2 the velocity of A, right? And now to get to acceleration, I'm going to take the derivative of velocity, right? With respect to time. So I'm going to take dvb over dt is equal to 0.5 dva over dt. And what do I get? The acceleration of B is going to be equal to 0.5 the acceleration of A. This is the equation, my fourth equation, and my second values for A and B, the accelerations of A and B. Does that make sense? So I now have 4 unknowns with equation 1, 2, 3, and now 4 here. Okay, so all I'm going to do right now is I'm going to take those 4 equations and I'm just going to write them out here so I have them handy. So I have equation number 1 was T1 is equal to 100 acceleration of A. Equation number 2, and you don't have to write out the step if you don't want to. I'm just on the back side and I don't want to flip my paper over constantly. Is going to be T2 is equal, minus 2940 is equal to a negative 300 AB. Oops, did we have a negative? Oh, we didn't. I'm so sorry. Look at this should be negative because this is going down. My mistake. So if you go back to block B, it should be negative 300 on this side because it's going down. I missed that negative sign. I'm sorry. And it's because the Y direction. Okay. So make sure that negative is there. Equation number 3. T2 is equal to 2T1. And then the last equation that we just did is AB is equal to 0.5 A acceleration of A. Okay, so now we've got 4 equations with the same 4 unknowns. This is solvable. Okay. So I don't know if there's one approach that you can take, but I'll tell you how I did it rather than trying to kind of, do the different iterations back and forth. So the first one that I did, I subbed number 4 into number 2. So I took number 4 here where I saw the AB and I put it up into number 2. So number 2 is T2 minus 2940 is equal to a negative 300. Instead of AB, I'm going to put times 0.5 acceleration of A. 0.5 acceleration of A. Okay. So now, even though I'm going to still have 2 unknowns, I'm just going to rewrite this. This is going to be T2 minus 2940 is equal to, this is going to be a negative 150. Forget your negative, Kelly. Acceleration of A. Okay. And we'll kind of sit here with this one. All right. That's as far as we're going to go. So the second one that I did, I substituted number 1 into number 3. So here's number 1, T1 is equal to 100 acceleration of A. So where T1 was, I put that there in number 3. So number 3 is T2 is equal to 2 times T1, but instead of T1, I'm going to put 100 acceleration A. Okay. So that means that T2 is equal to 200 acceleration A. Now, I'm going to take this 200 acceleration A, and I'm going to put it up in that equation right there where T2 is. Okay, so that means I'm going to write this over here. This is going to be, I'm going to put this at step number 3, and that's going to go here. For T2, I'm going to put 200 acceleration A minus 2940 is equal to negative 150 acceleration A. Okay, so in this equation, now I'm finally to a point where I just have the acceleration of A. So I can combine and solve for A. So I'm going to end up with, I'm going to pull the 150 over here. So it's negative 150. It's going to be positive on this side. So 350 acceleration A. And then I'm going to move my 2940 on the other side over here. Then I'm going to divide both sides by 350. And my acceleration A is going to be 8.4 meters per second squared. That's one of them. Okay. Now that I have the acceleration of A, I can substitute that into equation number 4 to solve for AB. So this is going to be my number 4. So I've kind of gone 1, 2, 3. This is going to be 4. And this is going to be acceleration of B is going to be equal to 0.5. And now instead of acceleration A, I'm going to put 8.4. Okay. So acceleration of B is going to be 4.2 meters per second squared. Remember, when you report your final answer, it has to be labeled with its variable equal to, and make sure you put your final units in there. Since this is acceleration, it's meters per second squared for both of these. Okay, so now I've got my accelerations. So now I'm going to do my tensions. Okay, I'm going to squeeze them in here. So this is going to be number 5. I'm going to do my T1 up at the top here, equation number 1. I know what the acceleration of A is. So T1 is going to be equal to 100 times the acceleration of A. So 100 times 8.4. T1 is equal to 840 newtons. Okay. And then number 6, I need T2. T2 is right here. T2 is equal to 2 times T1. So T2 is equal to 2T1. T1 is going to go up there. So that's going to be equal to 2 times 840. So T2 is equal to 1680 newtons. There we go. So those are our 4 unknowns using the 4 equations. And probably the one spot that you might have been like, this one right here, starting with that distance, okay? technically it's really kind of pulling back on what we had done the very first night and then getting to our acceleration. And once we had that, that gave us our fourth equation so we could solve for the four unknowns. Okay. All right. So that's example 12.3. Are there any questions at the moment on this sample problem 12.3? Okay. Then I'm going to stop the recording here.